Hi everyone, welcome to Orgo Essentials, not your basic organic chemistry tutorial, Episode 9, and welcome to Unit 2, Nomenclature and Alkanes. This unit will be an introduction to naming organic compounds, the properties of alkanes, and the characteristics of cycloalkanes. In this episode, we'll learn about the different functional groups common to organic chemistry, including their structure, their suffixes, and their properties in a reaction. Let's get started. The term functional group refers to the part of a molecule where reactions typically happen. These groups include concepts we've already learned, like double and triple bonds. Functional groups can even just be a single halogen atom. No matter what the rest of the molecule looks like, all of a certain functional group will have the same properties and characteristics. This is very useful because it allows organic chemists to make assumptions and classifications based on a molecule's functional groups. For example, if you see a hydroxyl group, shown here, then you know that part of the molecule is capable of hydrogen bonding. Not only does this save a lot of time, it is also very important for biochemistry, when molecules can include hundreds of atoms. Here is a list of all the functional groups we'll cover in this video. Just a bit of clarification before we jump into the functional groups. An alkyl group includes the hydrocarbon section of a molecule, the part consisting of just hydrogen and carbon atoms. Functional groups contain either an oxygen atom, a nitrogen atom, or a different bonding pattern than single bonds in a chain, such as a ring or double bond, something to differentiate it from the alkyl groups. First up is hydroxy groups, characterized by an OH bond. Hydroxy groups are hydrophilic, strongly polar, and can hydrogen bond. Organic compounds with hydroxy groups as their functional groups are classified as alcohols, with the general formula ROH, where R represents the rest of the molecule, assumed to be non-reactive or unimportant. An example of an alcohol is methanol, or methyl alcohol, often used as a solvent or as a fuel in car racing. Alcohols receive the suffix -ol. Secondly, compounds with amino groups are called amines. Amino groups are one of a few nitrogenous, or nitrogen-containing, functional groups in organic chemistry. They're characterized by the substituent NH2, with the general formula RNH2. Amines are basic, meaning they donate electrons and accept protons. Additionally, amines with up to 5 carbon atoms are soluble in water. Some examples of amines include methylamine, the simplest amine, and nicotine, a toxic compound in tobacco. Nicotine is an alkaloid, or a naturally occurring amine. Amines receive the suffix amine. Pretty easy to remember, right? Next, we have carbonyl groups, characterized by a COO bond. A compound with a carbonyl group can be one of two types of organic molecules, a ketone or an aldehyde. Ketones are classified as molecules with two alkyl groups bonded to the carbonyl group, represented by the formula RCOR'. Ketones receive the suffix -one, for example, propan-2-one or acetone. Aldehydes, on the other hand, are classified as molecules with one alkyl group, a carbonyl group, and a hydrogen atom, and can be represented by RCOH. Aldehydes have the suffix -al, or simply aldehyde, such as in propanal or propienaldehyde. In general, carbonyl groups are strongly polar and hydrophilic. Aldehydes and ketones with 4 carbon atoms or less are miscible with water, meaning soluble enough to form a homogeneous mixture. Compounds with carbonyl groups can hydrogen bond with alcohols, amines, and water, hydrogen bond donors. They supply the hydrogen of the hydrogen bond. Next, carboxylic acids are compounds that contain carboxyl groups. Carboxyl groups are characterized by a carbon atom double bonded to an oxygen atom with 2 lone pairs, with a hydroxyl group on the end, as shown here. This can be represented as both RCOOH or RCO2H. Though carboxyl groups are technically combinations of carbonyl and hydroxyl groups, carboxylic acids have totally different properties than ketones, aldehydes, and alcohols. They're fairly acidic, with a pKa of about 5, strongly polar, and strongly hydrophilic, allowing them to be miscible with water. Carboxylic acids get the suffix oic acid, but they're often referred to by their common names. Carboxylic acids can also form resonance structures in their anion form. This form is achieved by deprotonation, when this hydrogen ion is taken away, leaving a negative charge. For instance, when formic acid or methanoic acid, shown here, combines with water, that last hydrogen atom is taken, forming an ion like this. This anion can be drawn like this, or when we move the electrons in the double bond up to the oxygen, and the lone pairs on the side oxygen to the next door bond like this. This resonance stabilization contributes to the acidity of carboxylic acids. There are 2 functional groups derived from carboxylic acids, esters and amides. First, esters are the compounds that occur when the OH of carboxylic acids is replaced with an oxygen atom and a different alkyl group, represented by RCOOR', as opposed to the carboxylic acids RCOOH. This functional group is called a carboxylic group. Note that, in esters, the carbonyl group is still attached to an oxygen atom, so the properties of esters will be similar to those of carboxylic acids. One example of an ester is ethyl acetate, an industrial solvent with a distinct smell. Secondly, amides are the compounds formed when the OH of carboxylic acids is replaced with an amine group. Amides are characterized by a carboxamide group and have the formula RCONH2. Amides are not as basic as amines, but are fairly polar and soluble in water. One example of an amide is acetamide, the simplest amide, derived from acetic acid. Next, we have ethers, characterized by an oxygen atom between 2 alkyl groups. This structure can be represented by the formula ROR', where R' represents another alkyl group. Ether groups are polar, but cannot hydrogen bond with themselves, since they contain no OH bond. However, they can hydrogen bond with the hydrogen bond donors. To name ethers, combine the name of the alkyl group and ether. This nomenclature will be further clarified in later videos. A common example of an ether is diethyl ether, used for starting engines in the cold. That's it for this video. I've included a summary chart with all the functional groups covered so far. If you have any questions so far, feel free to email me or comment down below. The next video will be about basic alkane nomenclature. I'll see you then.